Now let's extend the 2D rotation to a 3D rotation. Now don't worry too much about the mathematics here. We will be talking through it, and you will also see it in a graphical format. So we're going to start off with a rotation around the z-axis. Now we don't have a z-axis so far, we only have our x-axis, which is a horizontal, and the y-axis, which is the vertical. So we're going to define a z-axis, and the z-axis is going to be the axis which is in towards and out from your computer screen. So what we've seen previously with a rotation round about the y and the x plane was in effect a rotation round about the z-axis. But don't worry too much, we'll see this just in a moment. Let's first of all talk through the equation. What we see here is the matrix equation for the rotation around the z-axis. It's very similar to what we've seen previously. We have our cos theta minus sine theta and cos theta, which we've seen in the two-dimensional case, and x1, y1, x0 and y0. But we've extended this to an extra dimension. Now the best way to see this is to actually just multiply out the matrices. So in order to do the multiplication, remember we multiply the row by the column, and we multiply the second row by the column, and we multiply the third row by the column. So the first row is going to be cos theta times x0, so that's going to give us x0 cos theta, and it's going to be minus sine theta times y0, so that's minus y0 sine theta, and that's going to give us the value of x1. We're going to have sine theta times x0, so that's x0 sine theta, plus cos theta times y0, so that's y0 cos theta. And the z0 term is 0. The third one here, we're going to have 0 times x0, 0 times y0, and we're going to have 1 times z0. So in this instance here, z1 is equal to z0. So again, we're going to put those into the graphical calculator, and you'll see those working, and we'll talk more about it. So don't worry too much about these equations. Now, the second equation here is going to give us the rotation around about the x-axis. And again, if you were to work through these and multiply the row by the column, the row by the column, the row by the column, you'll get these three equations here. Now finally, we're going to look at rotation around about the y-axis. And again, you can multiply out these matrices to get these equations here. So these sets of equations are the ones that we want to put into the graphical calculator. So let's go ahead and we'll do that now, and all of this mathematics will start to seem quite simple. Now you have access to this file, so you can go ahead and open it up and use it, or you can use it as a basis for creating a file of your own. Now I'm not going to put in all of the equations by hand like I did in the previous video because it just takes too long. So let's talk through the folders that we have here. So first of all, we've got an animation and an images folder. Now what I have in the images folder are 3 different images, and you can generate an image simply by going on to the add item and clicking on image, and it allows you to import any JPEG file, and you can adjust the size of that JPEG file. Now a useful thing here is that you also have an opacity. So this is going to change the value from the opacity from 0, which is transparent, to 1, which is fully visible. But what I've done is I've put a variable in here, and the variable is v_im1. And the variable appears up here within animation, and this is the slider called V_IM1, and you can see whenever I press the button here, you can see the equations appearing. So that's a neat little trick and quite useful if you're wanting to generate any videos. Now I also have 3 folders here, one for the matrix, which is the rotation in the z-axis, one for a rotation in the x-axis, and one a rotation in the y-axis. So the image up here for the equation is a rotation in the z-axis. So if I click on this here, you'll see I've just got this equation here and this equation here typed in. Now the only difference is the value for theta is no longer theta 0. I've actually called it theta_rad for radians because the value that we put into the equation is actually in radians. Now I still have the option here of actually putting the values in degrees. So we've actually got theta degrees. So whenever I adjust this here, I actually adjust theta in radians. So we can put it in degrees, but it actually goes into the equation in radians. And you can see that the conversion is done here, theta degrees to theta radians. And we've seen that in the previous video. Now, a thing to notice here as well is that we don't have the last term here, z1 is equal to z0. Now remember, z1 is coming out of the screen or in towards the screen. And in this instance here, whenever we rotate within that plane, it doesn't matter the value of z1 or z0, they're always going to be the same after the rotation. So we don't need to put the value z1 is equal to z0 in here. And we'll see that just in a minute. So I've done the same for the other 2 sets of equations. You can see here we're going to have the value for our rotation in the x-axis, and in this instance here we don't need to bother with the x1 is equal to x0. And we've also got the rotation within the y-axis. In this instance we don't need to bother about the y values because the y1 is equal to y0. So you see that I've got each of these sets of equations in each of these folders. Now we also have our inputs, which are going to be a value of 1, 1 and 1. So it's going to be along the horizontal axis by a value of 1, and up the vertical axis by a value of 1, and in towards the screen by a value of 1. So we can plot the value for our input. So the value for our input is x0, y0. Now I don't put x0, y0, z0 because we don't have a z0. We only have the 2 axes, which is the x0 and the y0. So the input is this point here. So right at the moment we don't have any kind of 3D engine, so we just have to try and imagine the fact that that point there is actually in 3D space, and it's actually going in towards the screen by a factor of 1. Now we're also going to have the outputs, so you can see the output in here, and you can see that we're going to have 3 different sets of outputs. So let's talk over those now. So we'll start off with a rotation in the z-axis. And again, this is the rotation that we've actually seen whenever we did the 2D rotation. So we're going to have an output x1, y1, and the inputs are going to be x0, y0. There is no z component here. So we're going to have the output, which is x and y, and I've put a subscript z because that's really telling us we're looking at the output in the x direction after a rotation around z, and an output in the y direction after a rotation around about z. So in effect what we have is, if we take the pencil here, we're going to have a rotation which is going to be in a anti-clockwise direction. Okay, so this is in effect just rotating around like this, and we're rotating in an anti-clockwise direction, and we're just generating a circle. So there's nothing new in this one. It's quite simple to see, and you can see why it is that the z component remains fixed. Because what would be happening with the z component is going to go in towards the screen and come out from the screen. So we can take slices in this direction towards the screen, and when we take slices in that direction, we're still going to see the same point rotating round about in a circle. So this is the reason why the value z1 is equal to the value of z0, and we don't need to put it in. So whenever we rotate this, we expect this point to rotate round in a circle. So if I click on the theta degrees, you'll see that does in fact rotate round in a circle as we would expect. So let's go on and we'll look at the next one, which is a rotation in the x direction. So these are the equations here for a rotation in the x direction. And you can see here that the value for x1 is equal to x0, so we don't use this, we only use these two here. So we'll put the point in for the output, and this is the output here. Now, what we're going to have is the x direction, which is the horizontal direction, and we're going to be rotating this on its axis, just like that. So if we imagine a point somewhere in space up here, whenever we rotate this round, this point is going to go round in this direction. So whenever we look in towards the point, what we're going to see is, rather than a circle, we're just going to see the point going up and down. So whenever we do the rotation here, we expect to see that point just going up and down like this. Now, when we actually go and do it, that is not what happens. So let's go ahead and we'll go through the simulation. So you can see that rather than the point going up and down, which is what we expected it to do, the point's actually still going round in a circle. And you can see why that is going to be, because we've only got two axes. We've only got a y-axis and an x-axis. So whenever we map out the point, we're mapping out the x points and the y points. But you'll note here that the output for this here is y and z. So what we've done is we've taken the y points and we've mapped them onto the x-axis. We've taken the z points and we've mapped them onto the y-axis. So in effect, what's happened is that instead of looking at this from this angle here and seeing this point going up and down, what we've done is we've mapped onto our x and y axis. So what we're actually doing is we're looking in from this angle here, and we're still seeing the point going round and round, because that's how we've mapped it onto our screen. So that's why you get this rotation here, rather than the point going up and down, which is what we would really like it to do. So let's go ahead and we'll see the final example, which is a rotation around about the y-axis, and we get the same sort of thing happening. So these are the equations for our rotation around the y-axis, and you can see that the y1 is equal to y0, so we don't need to bother with it. We've got our output, which is x1, z1, and the inputs here are x0 and z0. So what's happening here is we're going to rotate in the y-axis. So this is a y-axis here, and in effect we're rotating it around like this. So if we had a point, say here, and we rotated it in this axis, then that point is going to just work its way round like this. But if we're looking in from this angle here, all we see is this point. Rather than going round a circle, all we'll see is the point going back and forwards like this. So that's what we expect to see whenever we press the simulation. But again, that's not what happens. Whenever we press this simulation, the point is just going to go round in a circle again. So it does this for the same reason it did it for the previous example. In this example here, we expect this to go round in a circle like that, so it will map out just this line. But what we've done is we've mapped the Z onto the X axis, and we've mapped the X onto the Y axis. So what in effect happens is, instead of the point going round, the point still goes round like this, but we're no longer looking at it from this angle. We're now actually looking at it from above, coming down. And when we look at it from above, we still see it going round in a circle. So that's why this goes round in a circle. And it's not really what we're wanting. What we're wanting is for the point here to go around in a circle for one set of equations, for it to go up and down with another set of equations, and for it to go left and right with the third set of equations. So we don't want to look in this direction and this direction and this direction, because we're going to get a circle whenever we do that for each of those directions. All we want to do is look in the one direction, which is going to be the Y and the X plane and the Z plane towards the screen. So that means that if we look in only one direction, it means from the other two directions we're going to have to project the image onto the XY direction. So how are we going to perform that projection? Well, we're going to do that in the next video.